So we're Team OTTO, and I'm Coley Chapman, lead engineer.
I'm Samuel So. I am mechanical apprentice of Auto 1746.
And today we're going to be talking about the importance of manufacturability, how to make robots that are easy to build, assemble, and manufacture, and how all these parts are going to work together. So you might be thinking, what does it actually mean to be manufacturable? So we define manufacturability at Auto 1746 as the ability to create your parts, and the ability to replicate your parts, and the ability to assemble your sub-assemblies and your assemblies. So there are different levels. Oh, wait, go back, Sam. So we define manufacturability isn't like a binary thing, it's a scale. So there are some really easy to manufacture parts, like we say that 3D printed parts are really easy to manufacture because it's just a one-button thing. But some of the more complex parts might be a 5-axis mill part because it takes a lot more time and a lot more resources to make something like that. So a big question might be, why would you want your robot to be manufacturable? And the big thing this boils down to is time management. So you might be thinking that making a robot that's easy to build like this takes a lot of time in the pre-season and a lot of time in your design phase. But it's actually been proven that by doing this, you actually save a lot of time in your build phase and your assembly phase. So with designing, with assembly and creation in mind, you save time, but you also make it to where it's more replicable. So by utilizing computer-based manufacturing and designing things to be manufacturable to your skill level, you make it to where you can make a practice robot or make replacement parts very easily without having to worry about tolerances as much or worry about making sure that the two robots are identical. So the first step in this process is evaluating your resources, and this is a step that gets overlooked a lot. So every team has their own resource level, and this is something that you need to look at just for yourself. You can't ask other people for this. So the things you need to do is evaluate every resource objectively as you can. So you need to evaluate the pros and cons of each resource for manufacturing. So most of the time, teams will just look at the finished parts and decide, oh wow, this is really accurate, this can cut through a lot of things, but some of the things that teams won't think about is maybe it costs a lot to run that machine, it costs a lot of time to run that machine, and one of the big things that we overlook and other teams will overlook a lot is the accessibility of these machines or these these manufacturing techniques. So if you have a drill at your shop and that's all you have, your drill is worth a lot because it's extremely accessible and you can make things right now with it. We ran into, when designing parts for our sponsors or to be manufactured at other places, the lack of accessibility to those machines made them much more difficult to be manufactured on. And then once you've evaluated your resources and you have a good idea of what you have, some of the things that you can use for any part is designing for construction. And this is designing not just for manufacturing the part, but for assembling your entire robot or your entire sub-assembly. So one of the things that we forget a lot and we feel like teams should think about, and it's very easy to implement, is clearance holes. Whenever you're designing complex assemblies, the actual act of assembling them might be easy, but you might have a part that covers up access to part of your robot. These clearance holes are small holes that don't have any function except for allowing access to other parts of your robot. We also try and leverage identical parts in any sort of designing for construction because this makes it easier to not have to sort through parts. One of our big flaws this year was with our bumper design. We actually had brackets that looked almost identical, but they weren't. And this confusion led to much more difficult assembly time, and we lost time because of it. And it's an easy thing to design identical parts for your robot because a lot of the assemblies are just mirrored and multiplied. Another thing that's difficult when designing for construction, but there's a big return, is balancing your part count with complexity of parts. So this is a big thing that we struggle with sheet metal, and it's easy to make a part that can do everything, but that part's going to be so complex that it's difficult to manufacture. But on the other hand, it's easy to make an assembly that has 1,000 parts. By balancing complexity with your part count, you need to understand the limitations of your manufacturing techniques and also the limitations of your assembly skills. So to strike this good balance, you're going to want to try and minimize the part count while also minimizing the complexity of your parts.
So the first material we're going over is wood, and there's many different types of wood, but plywood is the most common type of wood used in FRC. And on the picture on the right, you can actually see 2415 team from PCH Wirecats, and during 2016. Large portion is made out of wood, and some pros and cons about wood is that it's very inexpensive, it's light, and it's durable, and it's a really ideal material to prototype with. Some cons are that it has the ability to expand due to climate, and it overall is not as sturdy as sheet metal. Next material is polycarbonate. This year we had to have an intake, and we used polycarbonate to make our intake. And the pros of polycarbonate is that there's a lot of different ways you can manufacture polycarbonate. You can CNC, water jet, or laser it. And we water jetted parts of our intake out here at Georgia Tech and CNC some parts. And you can also bend polycarbonate with a heat gun with a brake press. And the cool thing about polycarbonate is that it's elastic and it's flexible, so if your robot happens to run into another robot or a wall, it has the ability to return to its normal position.
Another material that we design with at Auto 1746 often is different types of milled plastics. So these plastics they can include PVC, but we also do a lot of dough and parts on our robot. The main way that we manufacture these parts is with a CNC. So the things you have to think about when designing with milled plastics is making sure that you can minimize the amount of material you're using. Most of these plastics are more expensive than your average FRC materials, so you want to minimize the amount of material you're using. And you're also going to want to think about how you're going to make these parts on your CNC or however you're cutting them. Some of the pros of this dough and plastic is that it's a little bit more flexible than your aluminum. So in this picture on the left, you can see that 2x1 was holding our elevator during the season, and that 1x1 was connected to our drivetrain. This more flexible connection with the dough allowed a little bit of flex with the elevator, so that if we ever fell over or got hit with our elevator, we wouldn't be bending aluminum plates like we would if we use normal construction for that. Some of the cons are it's extremely expensive, and some of these plastics can be toxic, so you're going to have to think about that when designing for this. So one of the most accessible ways to build your FRC robot is with extruded aluminum. And it's extremely versatile and rigid. So aluminum is actually light for how rigid it is, and these extruded aluminum bars allow you to create complex shapes with very little machining. And also rigid shapes because of their construction. So this aluminum, like I said, is extremely inexpensive, and it comes in two main types. So you'll see your 2x1, that's kind of like VersaFrame, that's a citrus circuits elevator. And you can see that's all made with 2x1. And then you also have your 80/20 style extrusion that's very common in prototyping. So one of the issues you'll see with aluminum is compared to plastics, it's actually kind of heavy. So it's not something that you're going to want to use for maybe an intake. And it's also inelastic, so if you use aluminum and it gets bent, there's no bending it back during the match. It's also extremely inexpensive, like I said, so it's very accessible for teams to build large assemblies out of aluminum extrusion like this. One of the main problems with 80/20 extrusion that you see right there is it's extremely dense. You can see how much of the inside is actually filled up with aluminum. So you're going to have to really consider if you're going to make an assembly out of 80/20 if you really need it out of 80/20 because of the weight. Going along with aluminum extrusion, aluminum plate is another type of aluminum that we use a lot. It retains a lot of the same qualities that I just mentioned with aluminum tube, but you can use it to make larger plates that can be used very similarly to polycarb plates. It's also inexpensive, costing a similar amount to any sort of aluminum extrusion. But using this, you're actually able to mill it on a CNC, laser it, or bend it. You can also cut this using a water jet. We cut it most of the time with a CNC at our in-house, and it can be used to make extremely rigid plates. So steel, while not used that often in FRC, we find that it has some extremely useful use cases every once in a while. One of the things you have to think about when designing for steel is it's going to take a while to cut through. So you're not going to want to minimize the amount of cutting time. So it's extremely rigid, more rigid than your aluminum is going to be, and it has an extremely high density and high weight. So it's also extremely inexpensive, less expensive than aluminum actually. So common use cases for us is ballast. This year our our robots are extremely tall and prone to tipping. Really inexpensive and easy way to do that is put steel on the bottom of your robot. But one of the places that we found it the most helpful is reinforcement to previous parts of our robot. Our robot this year was primarily sheet metal, and on places that we needed a little bit more reinforcement, we were able to add steel plates in order to make sure that those parts are going to move.
And 3D printing, it's really precise and it's actually really accessible. And on the picture of the right is a picture of a bearing block from this year on our elevator, which was made using SLA. But 3D printing is really accessible, such as FDM, the standard plastic extrusion, and that you can make parts in-house. And we actually had spacers on our intake, which was from the FDM, which is low complexity. And some common use cases of these are spacers, pulleys, and low load applications. Rubber. So this year in Power Up, we had to grab essentially power cubes, which are crates, and in order to do so, we use rubber wheels to facilitate grabbing those cubes. And on the top right picture, those are actually 5-inch Hella Space wheels from West Coast Products. And those typically go around for $50 per wheel. Depending on your team's budget, how much time you have. In our case, our team didn't have the biggest budget, but we had more time than money to spare. So what we actually did is, on the bottom right is a 12-inch by 12-inch neoprene sheet. And what we did is we water-jetted rubber wheels at Georgia Tech. And yeah, so that sheet actually only costed us $60, and we were able to make 9 wheels out of them, which is a lot more affordable than $50 per wheel. But on the other side, if your team has limited time but has money to spare, then the COTS is a better option because there's no time to and back from, let's say, Georgia Tech. And some pros and cons are that the pros, obviously, of COTS are that you have more complexity and you're also saving a lot more money. But cons are that if you're opting for COTS, you're actually using a bit more time than buying, let's say, Hella Space wheels from West Coast Products. And depending on your team, if you have more money than time, this can vary. And sometimes custom-made wheels are better, and sometimes buying them off the shelf is a lot better option. And off the shelf. So, like from the previous slide, like rubber, a lot of parts can actually be bought from VexPro, West Coast Products, and COTS can be important because if your team wants complexity custom parts are really important. But if your team has limited time but has the money, off the shelf is a lot better option, and it can also be outweighed by the lack of customizability can be outweighed by the resources saved.
So once you've decided on what material you would like to make your part out of, you're going to want to decide how you're going to machine it. And there's some best machining practices that you're going to want to follow when using these tools. And this helps improve the manufacturability of your parts. So one of the most common ways to manufacture things is a CNC router. These are becoming more accessible, and you can probably find access to one. So one of the things that we make sure to do is minimize our tool change. Our CNC router does not have automatic tool change, so every tool change that we add adds a little bit more inaccuracies to our part. You can see on this drawing in the bottom right-hand corner that this was a gearbox plate that we designed for our 2018 season, and you'll notice that all the fillets are 1/4 inch, and most of the holes are 1/4 inch as well. This allows us to do both our hole paths and our lightning paths with the same bit and minimize the amount of times that we have to change our end mill on our machine. One of the things that we also invested time into and helps the manufacturability and repeatability specifically of your parts is making sure that you spend time on designing a proper jig for your setup. This year, we did a lot of 2x1 extrusion for our first elevator design, so we actually invested in a set of clamps to hold our 2x1 extrusion in the exact same place every time. This makes sure that your part is going to be accurate, but more importantly, make sure that your part is repeatable. You're going to want to research your feeds and speeds for your CNC. This mainly affects how quickly you can make your part, but can also affect the accuracy. This is something that you're going to have to look at for yourself because every machine is different. One of the things that you're not going to want to do with your CNC and really can take away from final part is you're not going to want to leave your parts unsupported. So let's say you're designing a gear. One of the most popular ways to make sure that your part is, let me backtrack a little bit. The reason you don't want your part to be unsupported is after the CNC cuts out your plate, it's going to be loose and it will fly around or come out of the part. This is unsafe, but it can also make your part more inaccurate as it flexes. So one of the most easy ways to fix this is add tabs on the outside of your part, connecting it with a bigger sheet which you've already secured. On this gearbox plate, we did this with tabs because the outside doesn't have to be flat, but maybe or doesn't have to be perfect. But maybe you're manufacturing a gear or something where the outer face is extremely important. We actually would use mounting holes in that situation to be able to mount your part to the jig internally so that it doesn't fly around. With other types of materials, we've also utilized double-sided tape for quick wood materials and lighter materials like that. So we also leverage our laser cutter in our shop. It's extremely useful for prototyping and quick development, but one of the things that we recently have started learning about is our laser kerf. So the laser doesn't cut a straight line down, it also doesn't cut a zero thickness line. One of the important things about this is the laser can only be focused on one point, which means that you're going to have a sort of trapezoid in your cut shape. This isn't that important for most FRC applications, but if you're trying to make interlocking parts with your laser cutter, this can be something you have to consider. A common way to fix this is flipping your other parts so they interlock closer. We also try and design for one-step setup. Most laser cutters that we have access to don't have, or the laser cutter we have access to, and most laser cutters don't have any way to secure your material down accurately. So we make sure to design everything for one setup so that we don't have to manipulate the part later. We also have to optimize our laser speed. One of the big things that we spend time with is adjusting our feeds and speeds on our laser. Well, another mistake we had this year is overestimating the resolution of our laser system. So your gantry, which holds your laser, can only be so exact, and if you have it doing too many small movements in one time, it'll actually shake a lot, or that's something that we found, and it's also true for a lot of lasers that you have access to during FRC. So by optimizing for big, long, sweeping cuts, you're going to increase your resolution, and it'll help you make better laser parts. So in order to leverage your FDM 3D printer, which is something you're probably going to have access to during your FRC season, you're going to have to design parts with the manufacturing process in mind. And that's true for all of these. So the thing you're going to want to understand is your printer limitations and positioning, but also your infill. One of the things that gets overlooked, and one of the differences for designing for FDM 3D printing versus most other techniques, is your 3D prints aren't solid all the way through. This means that techniques like lightning holes are not going to be applicable to 3D printing because of the infill. You actually just end up adding more wall to your 3D print. So also printer positioning, this is something you're going to want to have to think about in the design phase. How is your part going to be printed? Are you going to have a flat side to be able to put on the build plate? Is it going to be extremely tall? All these are questions that you're going to want to think about before you start designing your part. You're also going to want to think about positioning of your features on your part. We found that holes that are vertical on the z-axis are actually much more clean than holes that are horizontal. This is because the extruder has to layer these holes, whereas it can smoothly do them with its gantry on the other way. This is something that you have to think about when designing your part, and is it really necessary to have holes on two faces? Also, these are just general 3D printing things, but make sure that you don't leave large unsupported overhangs. This will make your print fail, and it's something that you can't do, and it's something you're going to have to think about when you're designing your parts. So, for big takeaways from this presentation, you're going to want to make sure that you evaluate your resources as accurately as you can and as objectively as you can. This is the main thing I want you to take away from this presentation. Just because you have access to something far away or you have access to something that's costly doesn't mean it's always going to be the best option, because you have to evaluate not just the finished parts but also the entire process. So you're also going to want to choose the right material and the right manufacturing technique. You're not going to want to make your intake out of aluminum most of the time, and you're not going to want to make your drivetrain out of plastic. These are things that depend on each part and each assembly, but it's something you're going to want to think about. And finally, designing for construction and designing for manufacturing. This is making sure that your part even in its most basic design phase, you're thinking about how it's going to be made in the real world and how it's going to be assembled in the real world. This means maybe looking at your CAD before you assemble it and walking through how it's going to be made, or maybe making sure that you design everything to be plates so that it's easy to water jet or easy to laser or easy CNC. If you make sure to follow these ways to make your robot if you make sure to follow these rules for making sure your robot is manufacturable, you're going to have a better FRC season because you'll have more time for other things like coding, and you'll also have a more repeatable process to make parts. Thank you.
You talked a lot about materials that are good for manufacturability and construction. Did you guys ever run into any that were bad for manufacturability and construction?
Yes, definitely. Yes. So we also utilized acrylic in some of our prototypes, and we had some issues with manufacturability with that. On our CNC specifically, whenever we didn't get our Z-axis just right, you'd have a lot of flange left over, and that'd be dangerous and hard to replicate. Some of the things that we had difficulty manufacturing was the steel that we talked about. Making sure that those holes were accurate every time. That's not something we can put on our consumer grade CNC, so we had to do all those by hand. We used paper printouts to make sure that all the holes are correctly and one-to-one with our SolidWorks drawings. But even then, that amount of accuracy that you can get just at home or at school with your drill press is only so much. So one of the big things we had difficulty with was manufacturing with steel.
You talked about adding clearance holes.
Yes.
Did you learn that through experience?
Definitely.
By designing stuff that covered up part of your robot?
Definitely. Our intake this year was a plate and standoff approach. So it utilized water jetted plastic and it was held together by McMaster standoffs. One of the things we didn't realize was once you put the first two pieces together, putting the third piece on the bottom, you won't have access to the holes through the top piece. And so we had to end up drilling clearance holes for this or using right angle Allen keys in order to tighten this. So this is something that we implemented in later designs, and it's something that we definitely messed up on this year. Also our drivetrain, it had these pieces of 2x1 on it that were bolted in, and it was really easy to do it before you put the second sheet metal piece on, but once you put the second sheet metal piece on, we had to utilize special tools in order to get to it.
So you talked a little bit about how overall you save time by implementing these manufacturing practices. How much time do you feel like your team spent in the off-season and in the build season focusing specifically on manufacturability?
So during the actual season, we'll dedicate time during our CAD process to talking about how are we going to assemble this, how is it going to be repeatable, is this part going to be a part that you're going to want to CNC, is this a part that you're going to want to make out of plastic, and that's something that we'll do during the build season. But most of the training and practicing specifically for this comes from the off season. We'll make parts during the off season in order to test our machine capabilities, and we'll also design parts in order to teach more people how to design parts for these different machines.
In hindsight, what were the two least manufacturable parts on your robot from last year?
Let me think.
They can be either assemblies or parts or kind of.
Our drivetrain this year had, like I said, some clearance hole issues, but also some spacing issues with our gearboxes that made it really difficult to assemble. There's a certain way that you have to assemble it, and it's kind of hard to maintain. Also, let me think. This year was the first year we really thought about this, so I'm trying to think. Can you think of anything, Sam? What were difficult to assemble or design or make us?
The fact that with this on that whole elevator and that limited time it stayed.
Yeah. I really can't think.
Consider like elevator rails was really not enough for those two.
Yeah.
CNC, the access to CNCs for machining those.
Yes.
So those are trying to think of other good examples.
our V1 elevator utilized these large aluminum extrusion tubes. In order to lighten them to make our elevator faster, we cut this extremely large hole pattern on there. We originally intended to do this in-house, but our CNC is not large enough, so we had to outsource that to Georgia Tech, and it was an extremely time-intensive process. So in looking back, we would have designed better lightning patterns so that they're easier to manufacture, and also maybe realized that the lightning pattern might not have been as necessary.
Did you ever find yourself remaking a certain part a lot of times because it fails so often, or
Definitely.
changing materials because you realized something needed to be better for your robot?
Yes. So we pointed out in our presentation that we had those SLA 3D printed bearing blocks, and with our version 1 intake, we actually had some sort of like suspension on it, I guess you could say, to where those bearing blocks weren't in high load applications. But with our second revision of our intake, we went to that polycarb approach, and it's a little bit more rigid than the material we were using before and the design we were using before. So a lot of that force got transferred into those bearing blocks. They broke multiple times during competition, and we printed those on a Form 3D printer. So on a Form 2 3D printer. So we had those running pretty much every day making spares, so that was a quick change during competition. We later, with that design, moved on to aluminum bearing blocks that were milled actually at competition at the Georgia Power booth, which is another resource you can use. And those lasted the entire competition before we redesigned our elevator for the next one.
Can you talk about the 3D printers you guys have in-house and what you guys use each of them for?
All right. So the 3D printers we have in-house, we have access to 2 Form 2s, which are SLA machines, which means that they use a laser in order to cure resin. These can have extremely tight tolerances and accuracy. We also have access to 4 your normal FDM extrusion printers. They're Lowell's bots, and they're really good for prototyping and for low load, low accuracy applications. So the FDM printers normally get used for, like we said, bearing blocks with the tough resin, but also more complex parts. Whereas our FDM printers, we use those a lot for spacers because they require low accuracy. We also use those for any sort of large part that doesn't take a lot of load. So gearbox covers to keep dust out is something that we're looking into with our FDM printers.
So I noticed you guys didn't mention anything about welding your chassis. That's something a lot of teams do. How do you guys feel about welding your chassis and the pros and cons of doing that?
It's something we haven't ever investigated because we don't have access to any welding equipment at our school, and we're also not knowledgeable about it because we haven't researched it. So I can't really talk on that.
What are you planning to improve, or what's like the main thing you're planning to improve for the upcoming season in regards to manufacturability?
For the upcoming season, we actually mentioned that it's important to balance your part count and your complexity of parts. And this year we had a lot of parts that were complex and a lot of high part count assemblies. So we're going to try and minimize the complexity of our designs and minimize the part count of our designs to make them more manufacturable in the most basic sense. That's one of the big things we're working on this year. More large-scale manufacturability.
What's the process that you guys go through taking a part from CAD to coming off of your CNC?
For our CNC specifically, the first thing we'll do is look at the CAD model and decide how we're going to do it. So we utilize mainly a 1/4 inch mill for most of our applications, so we're going to make sure that the fillets are the correct diameter and that everything is going to work with the tooling that we have available. Second, we'll export that to a DXF and put it into our CAM program. DXF is a file type that's 2D, and in our CAM program, we'll set our speeds. We have set speeds for aluminum and set speeds for our plastics, so we don't have to evaluate what the best ones for those are for each of our tools. And then after that, the G-code file will be put onto our CNC, and that's when we start setting up our part on the actual CNC. So most of the time we'll utilize just bolting down our plate aluminum or plate plastic, but if we have, like we said, if we have a tube or larger thing, we actually have a jig set up so that we can get repeatable results on our CNC. After that, we'll run the G-code and After that, the part will come off. We'll utilize our deburring tool and belt sander to clean up the part a little bit, and then we'll be done. Yes?
You talked at the very end about how this is one of the first years you really focused on manufacturability. Why did you start that focus? What changed?
So, not this year, but the previous year, our robot was completely sheet metal made, or a majority made of sheet metal that's provided by our sponsor, Metcam. And as useful a tool this is, when I talked about accessibility and how close these machines are to your shop, Metcam is actually really far away, and their lead times are rather long for the 6-week build season. They can make amazing parts for us, but we struggle with manufacturability in the sense that we weren't able to replicate this at our own shop, and we weren't able to make extra parts, and we weren't able to iterate as quickly as we would like to if we had a more manufacturable robot design. So that's why we decided to look more into it for this year.
Thank you guys for coming. This has been TE Sessions with RoboJackets and 1746. So thank you to Coley and Sam for